Hello everyone, myself Darshani. I'm from Sri Venkateswara College of Engineering. Today's subject is Analysis and Design of Algorithm. The subject code is BCS 401 and the topic is 0 bar 1 knapsack. 0 1 knapsack problem. The knapsack problem is fundamental challenge in algorithm design and analysis, focusing on making optimal sections within constraints. This presentation explores the 0 1 knapsack problems, which restricts item selection to all items only, without fractions. We'll cover the problem definitions, solutions, approaches, complexity insights, and practical applications. Understanding this problem sharpens algorithmic thinking and prepares you for tackling real world optimization scenarios where resources are limited. The knapsack problem, an overview. Problem setup. A set of items is given, each with a specific weight and value. The goal is to fill knapsack to maximize total value without exceeding the weight capacity. Problem variations. 0 1 knapsack. Item either can be taken or not. Bounded knapsack. Limited quantity per item can only be taken. Unbounded knapsack. Unlimited quantity per item can be taken in that problem. Knapsack problem definition. Selection rules. Each items can be either fully taken or left aside. No partial selection is allowed, which means the item should be taken fully, but we cannot take the partially items so that it cannot be taken in the knapsack problem. Mathematical formulation. Given n items with weight w of I and value v of I, maximize total value summation of v of I into v of I x of I subject to weight limit, the limit where it goes to summation of w of I x of I where it is greater lesser than or equals to w. Variables. X of I belongs to 0 comma 1 indicates if the item I is selected 1 or not. Approaches to solve knapsack problems. Burette force. Check all possible subsets of items, guaranteeing an optimal solutions, but with exponential time complexity O of 2 power n. Dynamic programming. This method uses overlapping subproblems and optimal structure to solve efficiently for smaller scales, typically O of nw times. Big O of nw times. Greedy method. Quick but does not guarantee optimality of knapsack problem. Effective or fractional knapsack instead. Dynamic programming. Solution step by step. Table construction. Create a two-dimensional table dp of n plus 1 of w plus where entries represent max values with first I items and capacity j. Reoccurrence relation. If weight w of I is greater than dp of I into j is equals to max, excluding dp of I minus 1 into j and including item v of I plus dp of I minus 1. Otherwise, dp of I into j is equals to dp of I minus 1 into j. Dynamic programming example. Examples items weight weight 10, value 60, weight 20, value 100, weight 30, value 120. Knapsack capacity. The total capacity is 50 units. The table is filled row wise considering the item inclusion or exclusion. The result is traceback from table reveals the optimal combinations of minimizing and maximizing values within the capacity. Complexity analysis. Burette force complexity. The time complexity is big O of 2 power n, making it impractical for large item sets due to exponential growth. Dynamic programming complexity runs in big O n w where n is the number of items and w is the capacity. Term pseudo polynomial since depends on numeric input size. Space complexity. Dynamic program requires big O of nw space to maintain the table, which can be optimized in some cases. Optimizations and variations. Bounded knapsack limits item quantity solved within the adapted dynamic programming or other specialized method. Unbounded knapsack allows unlimited copies of each item, introducing different dynamic programming approaches. Approximation algorithms provide near optimal solutions faster for very large instances where deep dynamic program is costly. Real world applications, resource allocation, maximize project outcomes or production's value within budget constraint efficiently. Portfolio optimization selects investment to maximize return while respecting risk or capital limits. Cutting stock problem, reduce materials waste by optimizing cutting patterns for manufacturing. Cryptography subset some problem relates to knapsack solutions important in cryptanalysis and securing coding. Conclusion. Classical Classic optimization problem. The zero-one knapsack problem remains a foundational challenge in computer science and operational research efficiency through dynamic programming. Dynamic programming offers practical means to solve many instances efficiently, balancing time and computational space. Wide applications. From finance to manufacturing, knapsack algorithm guides decision in complex and constrained environment. Thank you.